Hello, you're very welcome to this video on RC circuits. Putting it all together, we derive the differential equation that models the output from the circuit based on an input voltage of constant value. I'm Seamus Bellew, and this video is for second year electronics students at DKIT Dundalk. So we'll make a start. So here we see an illustration of an RC circuit. The circuit contains a resistor R, and the units for resistance are ohms, and a capacitor C, and the units for capacitance are farads. We have an input voltage in volts and an output voltage in volts. And here's a photograph of a capacitor and a photograph of a resistor. So we set about deriving the differential equation associated with the circuit. That is also known as a low pass filter. The input voltage is symbolized by Vn, the input voltage, and the output voltage is symbolized by Vout, the output voltage. So we have Vn and we have Vout. So we recall Ohm's law. VR equals IR. The voltage across the resistor is equal to the current multiplied by the resistance. And likewise, a similar law applies to the capacitor. Vc is equal to Q over C, where Vc is the voltage across the capacitor, Q is the charge measured in coulombs, and C is the capacitance measured in farads. We also note that the current I is equal to Q divided by T, the charge divided by the time. The current is the rate of flow of charge, and an electron has a charge of 1.6 by 10 to the minus 19 coulombs, and this is a negative charge. So recall from first year, the velocity of a car as it travels along a road is given by S divided by T, where S is the displacement in meters from the base. Displacement corresponds to distance, and displacement also takes into account direction. And T is the time in seconds. So this formula here assumes that the velocity is constant, but as you know, when you're driving along roads or streets, you're constantly changing velocity, so it's not necessarily constant. So a car's velocity is measured by 1 revolution of the wheel. So the velocity can generally be given by ds over dt. V equals ds dt, where ds is a small change in distance divided by a small change in time. So effectively, the small change in distance is the length of the circumference of the wheel, and then the small change in time is how long that takes. And this speed gets transferred to the speedometer, so the driver is constantly being kept up to date as to what speed the car is travelling at. So again, recall the capacitor law that we had earlier on. The voltage across the capacitor is equal to Q over C, the charge divided by the capacitance. So if we cross multiply this expression here, we can see that Q is equal to C times Vc. So the charge Q is equal to the capacitance multiplied by the voltage across the capacitor. Again, we described the current as I equals Q over T. This was similar to the velocity, where the velocity was displacement divided by time, but this assumed a constant velocity, and likewise this is a constant current. So more generally, in correspondence where the velocity was ds dt, ds over dt, or the differentiation of the displacement. So v equals ds dt. In a similar way, we'll regard I is equal to dq dt. The rate of flow of charge changes with respect to time. And again, recall the relationship we have with Q above. Q is equal to C by Vc, the voltage across the capacitor. So these two now are important formulas, and we're going to use them now on the next slide. So again, recalling, I is equal to dq dt, that's differentiation. Q is equal to C by Vc. Now we can rewrite I is equal to d bracket of q dt. So q is the charge and it could be a function. And what we're going to do now is we know that q is the same as c times vc. And we're going to replace that q by c by vc. So you see that there now in this expression here. And the capacitance is constant, so that can get factored out. So we end up with I equals the capacitance C multiplied by dVc dt. So this is a differential expression. And from now on, we can use this formula as we proceed to derive our differential equation. So we don't have to worry about the derivation of it and the Q and the charge and so on. So most electronic engineers know this formula and they apply it when they need to apply it. So this is our circuit again. We've got a resistor and we'll assign a value to the resistance later on. That'll be 8 kilo ohms, and we'll assign a value to the capacitance, and that'll be 5 microfarads. And we'll also choose an input voltage, and we'll try and work out what the output voltage is. So again, these two relationships will be important. I is equal to C by dVc dt, the one that the electronic engineers know, that was derived from the charge and so on. And this is the basic Ohm's law. So we're going to use these two now, and we're going to set about deriving the differential equation associated with this circuit, this RC circuit, also known as a low-pass filter. So we'll make a start on deriving the differential equation. So we're going to derive a differential equation. So as we said, we're going to use these two formulae. Ohm's law, the voltage across the resistor is equal to IR, and I is equal to C by dVc dt. So here's our input voltage, our supply voltage. So from first year, you know that Vn is equal to Vr plus Vc. So the total voltage, as it were. So Vn is equal to Vr plus Vc. And we know that Vr, from Ohm's law, Vr is the same as IR. So now we can say Vn is equal to IR plus Vc. And now in the next slide, we'll look at changing I. We're going to substitute this in for I. So we'll build up our derivation as we go along. So we know that I is equal to C by dVc dt. So we substitute that in for that I there. So Vn is equal to C by dVc dt times R plus Vc. And now in the next slide, we'll just do a simple tidying up. We'll factor out the RC out front. So there you go. So Vn is equal to RC by dVc dt plus Vc. And that now essentially is our basic differential equation. It's got a differentiation term, dVc dt. We're going to be differentiating the voltage across the capacitor. With respect to time, the voltage across the capacitor will change as the time passes. But just to carry on with our derivation another little bit, we know that Vc is equal to Vout. So again, from first year, you might know that the voltage across the capacitor is equal to the output voltage. So all we're going to do, we're going to replace the VCs by Vouts. So Vn is equal to RC by dV out dt plus Vout. So their output voltages now. We've got the RC term is dV out dt equals Vn. And this arrow here just indicates we're going to swap the left-hand side and the right-hand side around just to get our final expression. And that'll be our final differential equation. So here we go. RC by dV out dt plus V out equals Vn. And that's our differential equation associated with our circuit. Now this is a general expression of the differential equation. It hasn't actually taken into account yet that R is the 8 kilo ohms and C is the 5 microfarads. So for our particular circuit then, we have R equals 0.8 kilo ohms, which is 800 ohms. And in engineering notation or scientific notation, that's written as 8 by 10 squared ohms. C is 5 microfarads, 5 by 10 to the minus 6, so 0.000005 farads. So you're used to calculating the RC time constant. So when we multiply these two values together, or you can take them in the scientific form, 8 fives are 40, 10 to the minus 6 by 10 squared is 10 to the minus 4. 40 by 10 to the minus 4 is the same as 4 by 10 to the minus 3. So the RC time constant is 4 milliseconds. So we're going to take our input voltage to be 6 volts, and we've now just figured that our RC time constant will be 4 milliseconds. And taking the differential equation and solving it, doing the mathematics on it, we haven't done that yet, but we'll just look at the output voltage from the differential equation. So we'll come back in a week or so and come back and solve the differential equation. But just for today, we'll take the answer out from the differential equation and just work with it and see that it corresponds to some of the theory that you did in first year. So the output voltage from our RC circuit corresponds to V out equals 6 by 1 minus e to the minus 0.25 t. And that takes into account this RC time constant. So again, to summarize where we're at with all that, this is our general differential equation. RC is 4 milliseconds, so we substitute 4 in for RC. So this is going to be our particular differential equation for this circuit here with the R and C value. So 4 by dV out dt plus V out equals, and the input voltage is 6. So solving that differential equation, doing the maths on it. So we're not going to do that today, but we'll give it the answer and we'll do a little bit of checking. So that's the output voltage from this circuit at any time t. So now we're going to look at some examples of that then. So here we are. We're now going to check the answer to our differential equation. So here's the differential equation that we derived for the particular circuit that we're looking at. And here's the answer that we suggest comes out of the differential equation. So again, to repeat, you're not quite sure where that came from. But what we're going to do is we're going to check that it is the correct answer. So at least you'll believe after this that it is the correct answer. So in a week or two's time in class, we'll come back and show you how to solve the differential equation. So this is the answer. V out equals 6 times 1 minus e to the minus 0.25 t. Let's just multiply out that expression there. So V out is 6 minus 6e to the minus 0.25 t. Now this differential equation here says 4 times dV out dt. So just differentiate this expression. What's dV out dt? dVO dt. The O symbol symbolizes out. And that's equal to differentiating 6 and we get 0. And you know the rule for differentiating e to the power. Bring the power down in front. So minus 0.25 by minus 6 gives us plus 1.5 e to the minus 0.25 t. The power doesn't change on the e when we differentiate. So piecing that together then. So look at the left hand side of the differential equation. We have 4 times dV out dt. So 4 times dV out dt equals 4 of these here. 4 times dV out dt. 4 times 1.5. 4 times 1.5 is 6 e to the minus 0.25 t. So 4 dV out dt plus V out, and we know what V out is. It's 6 minus 6 e to the minus 0.25. So just rewrite that out. So we got 4 dV out dt plus V out. That's the left hand side. So if we add those two guys together now, that's going to give us that left hand side there. And we're hoping to get the left hand side. And you can kind of see that 6 there and that minus 6 will cancel each other out. And it looks as if we're in business. So adding the left hand side out, we get 4 dV out dt plus V out equals 6. And that's the differential equation that we have up there. So we've checked that our answer to that differential equation is the correct answer. So you can take it that we have the correct answer, even though you're not quite sure how we solved the differential equation. So that's another day's story. So now that we have the output voltage at any time t from our circuit, we can substitute any time we like into this expression. So if t is equal to 8 milliseconds, 2 time constants, so we substitute 8 in for t. So V out equals 6 by 1 minus e to the minus 0.25 times 8. Put that into your calculator and work it out, and we get the output voltage is 5.19 volts. So remember, our input voltage was 6 volts, and you would have learned percentages in first year. So after 2 time constants, 5.19 divided by 6 multiplied by 100 gives you 86%. So this is the output voltage, and the opposite of the 86%, if you take 86 from 100, it's 14%. Again, you can put any time you like into this expression, not just time constants. The time constant is 4 milliseconds. Two time constants would be 8, 12, 16, and so on. But you don't necessarily have to work with time constants. You can substitute any time you like. So here we just pick another example. T equals 1.6 milliseconds. Substituting that in, working our way through, we get that the output voltage after 1.6 milliseconds is 1.98 volts. So as we said in the derivation of the differential equation, V out is the same as VC. So V out is 1.98 volts. VC is also 1.98 volts. But do you remember at the beginning we said Vn is equal to Vr plus Vc. So the voltage across the resistor plus the voltage across the capacitor is equal to Vn, which is the 6 volts. So taking the 1.98 away from 6, we can also work out the voltage across the resistor at the time of 1.6 milliseconds, and that's 4.02 volts. So at any time t, the VR and the VC is always equal to 6, the input voltage. Okay, so let's look more closely at the RC time constants. The RC time constant, as we said, was 4 milliseconds. So after one time constant, it's 4 milliseconds. Two time constants, 8 milliseconds. Three time constants, 12 milliseconds. Four time constants, 16 milliseconds. Five time constants, 20 milliseconds. The input voltage is always 6 volts. It's constant, so that never changes. So all these times here, the input voltage will be 6 volts. Here's the output voltage that we established from solving our differential equation. Let's calculate V out at the various time constants. So here we check what happens after one time constant at 4 milliseconds. We also check what happens at time equals 0. Substituting 0 in for t, you get e to the 0, which is 1. 1 minus 1 is 0. By 6 is 0. So at time 0, the output voltage is equal to 0. And accordingly, the input voltage was 6. So the output voltage and the voltage across the resistor always add up to 6. So that's why VR is equal to 6 there. Vn is always equal to 6. It's constant. Now after one time constant, 4 milliseconds, substituting 4 in for t, we get e to the minus 0.25 by 4 corresponds to e to the minus 1. And you can check that out, and we'll verify it now in a few minutes. The output voltage will then come out to be 3.79, and then the voltage across the resistor then has to be 6 take away 3.79. So we generate this table now for the various time constants up to 5 time constants. So again, here's the details. Going up in steps of 4 milliseconds, t equals 20 milliseconds corresponds to 5 time constants. The input voltage is always 6 volts. The output voltage is increasing, and eventually after 5 time constants, we more or less regard the output voltage as corresponding to the input voltage. And you can see in a corresponding way in the opposite sense, the voltage across the resistor decreases, and eventually after 5 time constants, the voltage across the resistor is negligible. Okay, so here in this slide, we're just expanding the detail on the previous slide. So we just want to look at these percentages here. This is the V out, the solution of the differential equation gives the output voltage at any time t, and we know that V out is the same as VC. So VC and VR always adds up to 6. So VC and VR always adds up to 6. V out and VR will always add up to 6. So basically what we're saying is, if this is the formula for V out, the formula for VR will be equal to 6 minus V out. So VR is 6 minus all this here. So minus 6 by 1 minus e to the minus 0.25t. So VR is equal to 6 minus 6, and minus 1 minus is plus 6 e to the minus 0.25t, and that 6 and that minus 6 cancel out. So VR has simplified down to 6e to the minus 0.25t. So there's the formula for the voltage across the resistor at any time t. We already knew the figures for VR because we took them away from 6 from the results for V out, but now we can see that the results for VR expressed as percentages of the 6 out of 6 is 100%, 2.21 is 37%, and so on. But you can see that those percentages are precisely related to the powers of e. E to the 0 is equal to 1, which is the same as 100%. Just multiply these by 100. After one time constant, it's e to the minus 1, which is 0.37, 37%, and so on. Okay, and then in the next slide, we just get the corresponding percentages for V out. So if we take 100%, take the VRs away from 100, so the initial output voltage is 0. After one time constant, it's 63% because the VR was 37%, and so on. So that explains the percentages that you'd have learned in first year. So here's a graph then for the output voltage. Again, these percentages only work for an input of a constant voltage. So after one time constant, 4 milliseconds in this case, the output voltage was 3.79 volts, which corresponded to 63%. Two time constants, 8 milliseconds, the output was 86%, and so on. And eventually, after 5 time constants, we see that the output is more or less 100%. Technically, it's 99%. So that's the differential equation that we derived for our particular circuit, and this was the solution for that differential equation. And finally, we could ask the question, when is VC equal to 4.2 volts? Or when is V out equal to 4.2 volts? So we know that VC is equal to 6 by 1 minus e to the minus 0.25t, substituting 4.2 in for VC, divide across both sides by 6, 0.7 equals 1 minus e to the minus 0.25t. Take 0.7 away from both sides and add e to the power of 0.25 to both sides. So we get e to the minus 0.25t equals 0.3. Take the ln of both sides. Minus 0.25t is the ln of 0.3, which is minus 1.204. Divide both sides by minus 0.25. So t equals 4.816 milliseconds. So finally, looking at the graph of that then, so the voltage VC or V out is 4.2 volts after 4.816 milliseconds. So that concludes this video. We hope you've enjoyed it, and we look forward to solving these differential equations in the near future. Thank you very much.